Welcome to the distinguished lecture series of the Indian Mathematics Consortium. The aim here is to host virtual colloquia by some of the best researchers and expositors around the world. The speakers are carefully chosen by the scientific committee from among mathematicians who are not only distinguished researchers but are also known for the quality of their exposition. The principal aim here is to make the talks as widely accessible as possible, especially to PhD students. With this in view, the format of most of the talks will be in two stages. First, there will be a pre-recorded talk by the speaker, which will be posted online. Interested audience can then view this at their leisure and communicate questions, if any, to the organizers. The second stage will be a live interactive session between the speaker and interested participants, and that will be held about 2 weeks after posting the online talk. The approximate duration of the talk will be about 45 minutes, and that of the interactive session will be about half an hour. The Distinguished Lecture Series is co-hosted by IIT Bombay and ICTS Bangalore. Welcome.
Hello and welcome to this lecture. It is my distinct pleasure and honor to introduce today's speaker, Professor Neena Gupta. I have known Neena since she was a graduate student, and it has been a pleasure and a delight to watch her grow into one of the finest young algebraists in the country today. Neena obtained her PhD in the year 2011 from the Indian Statistical Institute, or ISI, Kolkata, under the supervision of Professor Amartya Datta. She is currently an associate professor in the Theoretical Statistics and Mathematics Division of ISI Kolkata. She has many beautiful works to her credit, and I mention in particular her remarkable solution of Zariski's cancellation problem for the affine space A3 in positive characteristic. She answered this long-standing problem in the negative. For these and many other works, she has received numerous awards and professional recognitions. I will just name a few. She was a recipient of the Indian National Science Academy Young Scientist Medal in the year 2014, just 3 years after her PhD. She received the Swarn Jayanti Fellowship from the Department of Science and Technology, or DST, of Government of India in the year 2015. She received the prestigious Shanti Swarup Bhatnagar Award in Science and Technology in the year 2019. Just last year, she received the DST ICTP IMU Ramanujan Prize given to young mathematicians from developing countries and sponsored partially by the International Mathematical Union together with ICTP in Italy and DST of Government of India. She is an invited speaker at the International Congress of Mathematicians this year, 2022, which was to be held in St. Petersburg. I think it will still happen virtually. And just earlier this week, to be precise, on 8th of March, the International Women's Day, she received what is called the Nari Shakti Puraskar, which is a woman empowerment award given to women who have done significant contributions across different fields, and she received this from the President of India. So as I said, it's a great honor that for us that she has agreed to give this lecture in the TMC Distinguished Lecture Series program, and she will speak to us on GA actions and their applications. Over to you, Neena.
Good morning, everyone. Today I'm going to talk about GA actions and their applications. GA is the additive group K plus for a field K. The K plus is an additive group, and that group action acting on affine varieties and their applications. At first, I would like to apologize because this talk is very basic and it's an introduction, you can say, maybe only newcomers or students can find this talk a little bit of some material, and it hardly contains much input for the experts in the area. So I will talk on this area. And so the key words in my talk which will come across is GA actions. So GA action has its equivalent formulations, exponential maps, which we can talk of on arbitrary rings, and local important derivations on rings containing the field of rational numbers. So there are some major breakthroughs in the area of local important derivations and exponential maps. Mainly they are the characterization of the affine plane by Miyanishi, which led to the solution of the Zariski's cancellation problem for the affine plane in 70s. The solution of the linearization conjecture by Russell-Koras, Makalimanov, and Kaliman, and basically they proved non-triviality of certain threefold, which was in very important problem at that time, which was proved in 1990s. And the third major breakthroughs was proving the non-triviality of this asynchronous threefold, which led to the solution of the Zariski's cancellation problem for the affine 3 space in positive characteristic. So before that, we first define the concept of GA actions. So throughout my talk, K will always denote a field. For defining GA action, it is better to assume that K is an algebraically closed field, but most often it is not necessary. V is an affine variety over K, and GA is this additive group K plus, which you can also realize as a linear subgroup of this group GL2K, which is a reductive group, and GA is then an unipotent subgroup of GL2K. Any GA action on a variety V is nothing but an algebraic action of the additive group. So it's a group action on the variety V, which so the group action satisfies this identity axiom that of the identity element of GA is 0. So theta of 0x is x for every x in V, and theta of this additive group action. So this additive action map. So this is alpha and beta. If you apply first beta and then alpha, then this is alpha plus beta. So this is the additive action. So these two axioms are basically the actions, means group actions. And when I say it's an action on a variety, I mean that they are algebraic actions. So that means this theta is a morphism of varieties. So this group action has been a very important and central topic of research right from the 19th century. So studying group actions on a variety and to study the ring of invariants had been a very interesting topic. In fact, if you know this Hilbert basis theorem, which was proved by Hilbert in 1890, was an outcome, or I would say it was an outcome on his study of the invariant theory problem, which actually led to the solution of a fundamental problem in an invariant theory. So it was on the basis whether the ring of invariant of a certain group actions are finitely generated or not. So Hilbert's 14th problem, see, Hilbert has listed down some 23 problems in the ICM 1900, and there he had listed down some 23 open problems for the mathematicians of the 20th century to attack and to work on them. And one of the problem, this 14th problem, was also originated from the theory of group action on an affine variety. And so the first major result on an Heisenberg, and so Maurer had given a proof in as early as in 1899, and this was there was a gap in the proof which was taken care by Witzenberg in 1932. Finally, Sheshadri gave a complete proof in 1962. So they proved that over a field of characteristic 0, if GA is acting on an affine variety by linear transformations, then the ring of invariant is certainly finitely generated. So this is a result which tells you that the study of GA action on an affine variety is a very early subject, and many people, many big people have been studying this for a quite long time. So this is one of the main theorem in the study of algebraic group actions. So this result says that if G is linear algebraic group of the GL and K, then these two statements are equivalent. That is, the ring of invariant KVG is finitely generated for every algebraic action of G on V if and only if G is a reductive group. So no matter what action you have taken, if the ring of invariant is always finitely generated, then G must be a reductive group. So, and the converse is also true. So this was proved by Nagata. This implication 1 implies 2 by Nagata, and Popov in 2 implies 1. So in some sense, and this result for finite group was settled by Amy Noether. So nowadays it may be taken as a standard exercise for people studying integral extensions and in commutative algebra, but it is it's a noteworthy result for a finite group, and Amy Noether gave a complete proof of this. So as you can see that this statement that the ring of invariant is finitely generated if and only if the group G is reductive, completely in some sense shattered the study of the GA action, because GA is in very much an unipotent group. So it is complement of reductive group. So certainly it means that the ring of invariant of a GA action need not be finitely generated. And there are explicit examples which have been given by Nagata and so many people. So therefore, this concept of a study of a ring of invariant of GA actions was thought of to be something peripheral or pathological, and it was not interesting to many researchers because they just don't have any handle or control over the ring of invariant. So it became a little bit of unfashionable outside a limited circuit. However, many big people like Gabriel, Noyes, Rensselaer, Dixmuir, they have been contributing in this area by proving many important results. The first major breakthrough in the area of GA action was achieved by Miyanishi. He was probably the first researcher to study or investigate GA action systematically. In his book, TIFR book 1978, he highlights the concept of loco-important derivations and proved many important theorems on loco-important derivations, which led him to the many important breakthroughs in the area of affine algebraic geometry, namely the classification of the affine surfaces, characterization of the affine plane, and which eventually led to his solution of Zariski's cancellation problem for the affine plane. Later in 1990s, Makalimanov, Devney, Finston, Vandenassen, Kaliman, Degley, Frodenberg, Duxon, Douglas, Bhatwadekar, and Datta, and many subsequent researchers have been contributing in this area rigorously from 1990s. And I'm sorry if I'm missing a few people, but there have been many important results and discoveries by these people. Let me first tell you about the major breakthroughs which have been achieved using GA actions on an affine variety. The first major breakthrough which was achieved was the solution of the Zariski's cancellation problem for the affine plane. Here we use a version loco-important derivation, which is a version of GA action. So it helped in this loco-important derivation, again helped in the solution of the linearization conjecture. So this was a conjecture which was posed by Kambayashi in 1976, and it remained an open problem for a long time, at least for 2 decades. The solution of this C star action on C3, it took almost 2 decades for many big people to solve it, and finally it was solved. And so a solution C star, as you see, is a reductive group. So the study of this reductive group actually brought in the study of the unipotent group. So unipotent group, so those are not considered to be good groups. So the solution of this C star action, actually this linearization problem, actually had to go through this study of the C plus action on that affine variety. We will be discussing this. And recently, we used exponential maps, which led to the solution of the Zariski cancellation problem in positive characteristic in higher dimension. So thus, from these 3 major breakthroughs, one can see that the study of this additive group or this GA actions is not something to be should not be looked below, or means something not unusual. In fact, certain invariants of the GA actions, or there are quite useful things which may help in proving major problems in affine algebraic geometry, and it could be a part of a general armory of algebraists and geometers, may not be just confined to specialists. So we now begin with the formal definition of GA actions. So this we have seen. So K is an algebraically closed field, B is an affine domain, V denotes the max spectrum of B that consists of all points which are maximal ideals of B, and G as the additive group K plus. So it's a group along with an algebraic this variety structure, ring theory structure, and the action of G on V is a morphism of affine varieties which satisfies the two axioms of the group actions. So another definition which I can say is of exponential map. So let K be an algebraically closed field. For this you don't need K to be a field of characteristic 0 or algebraically closed. So K is any field and B is an K algebra. So the exponential map on B is a K algebra homomorphism from the ring B to the ring BU, which satisfies those two axioms. That is, the first axiom is if you have this map phi U and this map evaluation map U to 0, then this composition is identity. So this is that evaluation map. And if I denote phi U for this indeterminate U, then phi U composed with phi V. So phi V is the map from B to BV, and U is sent to U as just identity. So this composition is nothing but phi V plus U. So if we look at it more carefully, translate it into algebraic geometrical situation, then when K is an algebraically closed field and B is a finitely generated K algebra and V is the max spectrum of B, then this GA action on V is nothing but the exponential map on B. So you can see the study of GA action on a variety is equivalent to the study of exponential map when K is an algebraically closed field and B is a finitely generated K algebra. So whether you study the group action or whether you study this kind of K algebra homomorphism, you are doing the same thing. Another definition is locomotion derivations. So derivations we are all comfortable with. So D is a derivation, is a K-linear map from a ring integral domain B to B, which satisfies this linearity rule, this K d of x plus y is dx plus dy, and this Leibniz rule that d of xy is x dy plus y dx for every x and y in B. A derivation D is said to be a locomotion derivation if it satisfies that for every element x in B, there exists an integer n depending on x such that nth derivative of x is equal to 0. So that is why this name nilpotent, that it annihilates an element x after some time. So this x may depend on, this integer n may depend on the element x. So locomotion derivation may be thought of as a partial generalization of the partial derivative. So you have seen del del x on a polynomial ring. So they are the examples of locomotion derivations. We will denote LND of B, the set of all locomotion derivations on B. Now we will see that this concept of locomotion derivations and exponential map are same as the study of GA actions. So we assume that the ring B contains the field of rational numbers. K is an algebraically closed field. Then any exponential map phi U from B to BU, which is given by a ring homomorphism. So it sends an element B to a polynomial in U. And because of this identity condition, B, the coefficient constant term is B itself. So any such exponential map will give rise to a locomotion derivation, which is the coefficient of U. So if I set d of B equal to B1, which is the coefficient of U, then D will be a locomotion derivation. So this is an exercise and it's not difficult to check. In fact, we can see that B of Bn, the nth coefficient of U to the power n, is nothing but the nth derivative of B divided by n factorial. So this division by n factorial is needed. Therefore, we need Q is contained inside B. Conversely, given any local-important derivation d from b to b, we can construct an exponential map phi u from b to bu by this and using this formula. So this thus the study of exponential map is same as the study of local-important derivations. Further, an element b is in the kernel of a local-important derivation if and only if you can see from this that phi u of b is b, that is b is in the ring of invariant of phi u. Further, thus over an algebraically closed field of characteristic 0, a G action on a variety V is same as the study of exponential maps on B, which is same as the study of local-important derivations on B. And the study of ring of invariant of a G action is same as the ring of invariants of an exponential map, which is same as the study of kernel of local-important derivation on a ring B. So we have now understood that the G action is has two equivalent formulations, local-important derivations and exponential maps, which are all same when K is an algebraically closed field of characteristic 0. Now we come to this first major breakthrough, that is the algebraic characterization of the plane. So let K be an algebraically closed field. So the Zariski's cancellation problem for the affine plane asks whether if the polynomial ring over a ring B is isomorphic to a polynomial ring in 3 variables, does this imply that B is isomorphic to the polynomial ring in 2 variables? So this problem was named Zariski's cancellation problem. And in his attempt to solve this cancellation problem for the affine plane, the great mathematician from TIFT, C.P. Ramanujam, he gave an proved a very important result. He proved this, gave a topological characterization of the affine plane. And subsequently, Miyanishi gave the following algebraic characterization using local-important derivations. So Miyanishi, again, in his attempt to solve the cancellation problem, he proved that when K is an algebraically closed field of characteristic 0 and B is a finitely generated K algebra of dimension 2, such that B star is K star, the units of B is same as the units of the field K. B is a unique factorization domain, and there exist a non-zero local-important derivations on B, then B must be a polynomial ring in 2 variables over the field K. So as we see that if it is given that B1 is K3, then from this we can immediately conclude that B is a finitely generated K algebra of dimension 2. The units of B is same as units of K, and B is a unique factorization domain. Thus, the solution of this Zariski's cancellation problem eventually reduces to prove that there exists a non-zero local-important derivation on B. Fujita, Miyanishi, and Sugi, they gave a solution to this cancellation problem. They proved that if B is a K algebra such that B1 is K3, then B is K2. This result was further generalized in arbitrary characteristic by Peter Russell over perfect field, and then we later did it on any arbitrary field. So this solution was achieved by, as a subsequent, the major result which they used was a Miyanishi's algebraic characterization using local-important derivation. And their proof is very beautiful, but it involves so many ideas which are not usually self-contained. So Makalimanov very recently in 2008, he gave a simple self-contained proof using just local-important derivation, and I will be just giving a brief illustration of that proof. So what Makalimanov did is he defined an invariant, so which is associated to a local-important derivation. So given any ring R, he defined the subring of R, ML of R, which is intersection of all kernels of D, where D varies over all the local-important derivations on the ring R, which is same as the intersection of R phi, where phi varies over all the exponential maps on the ring R. So Makalimanov, he called this subring the AK invariant, and it is nowadays it is known as ML invariant. And this is an invariant of the ring. That is, if you have any automorphism of the ring, it will fix this subring. For example, if you have the polynomial ring Cxyz, then it is easy to see that the Makaliman invariant of Cxyz is C, because you have the three locomotion derivation, the partial derivatives given by del x, del y, and del z. And if an element f is in the Michelman invariant, then derivative with respect to x, y, and z must vanish, and therefore f must be a constant function. So therefore, it's usually it's not so easy to compute the Michelman invariant of any arbitrary ring, but for polynomial rings, these are very easy because of the presence of partial derivatives. We now give a proof due to Kreshela and Michelman of this cancellation problem for the affine plane. So for that, we will be using this lemma. So let B be an affine domain over a field K such that there does not exist any local important derivation on B. So B is a ring which does not admit any non-zero local important derivation. Then they proved that the Michelman invariant of B1 is B. The proof is quite elementary, but of course it's not so easy. But this proof is quite useful. This result is quite useful. It immediately solves the cancellation problem of Fujita, Miyanishi, and Sugi. So note that if B1 is K3, then B is finitely generated of dimension 2. The units of B is same as units of K. And B is a unique factorization domain because B is a retract of the polynomial ring K3. And retract of an UFD is a UFD. And all we need to prove is that B admits a non-zero local important derivation using Miyanishi's algebraic characterization. And now my claim is that B actually admits a non-zero local important derivation, because if it does not, then Michelman invariant of K3, which is a polynomial ring, must be K, as we have seen before. And therefore, by this result, Michelman invariant of B1 cannot be B, because Michelman invariant of B1 is K. So B1 cannot be B, and therefore B must admit a non-zero local important derivation, and hence the proof. Therefore, B must be K2 by Miyanishi. This algebraic characterization of the affine plane. Similarly, let's say following Miyanishi, we tried to give an algebraic characterization of the affine 3 space with by Nikhilesh Dasgupta. So we defined ln star of B, the collection of all local important derivation whose image contains 1. So these are the derivations which having the slice, and we define, so this ML star of B is the intersection of all the kernels of D where D varies over LND star of B. So this ML star B has been defined in this Frodenberg's book 2006, and we call it the Frodenberg-Michelman invariant. And using this invariant, we obtained the following algebraic characterization of the affine plane and the algebraic characterization of the affine 3 space. So we proved that if B is a finitely generated K algebra of dimension 2, then the following 3 statements are equivalent. That is, B is a polynomial ring in 2 variables. If and only if B admits local important derivation whose image contains 1. Sorry, this ML star of B is K, and which is same as saying that the B means this Michelman invariant of B is K, and B admits a non-zero local important derivation having a slice, having whose image contains 1. Similar such characterization is also true for the affine 3 space if we have further assume that B is a unique factorization domain of dimension 3 over an algebraically closed field. None of these hypotheses that K is algebraically closed or B is a UFD can be dropped. In fact, this characterization also cannot be extended to dimension 4. So this is what we had shown for an attempt to give a characterization of the affine 3 space. This is the result which we have shown. Now we come to this Russell-Koras threefold. So this ring A, it's an hyperplane hypersurface in K4. So it's given by this equation, which equation looks quite simple because it's linear in Y, and the degrees are also not very high. So this is a very simple equation. And this was a major important problem in 90s, whether A is a polynomial ring in 3 variables over C. And why it was so tempting to believe that A is actually C3? Because This ring A is a regular ring. It's a unique factorization domain. The units of A are same as units of C. It has a dominating map from C3. So in some sense, it is sandwiched between two C3s. All projective A modules are free. Further, this variety given by this ring A, which is a zero set of this polynomial, is diffeomorphic to R6. And V has logarithmic Crotard dimension minus infinity. We just recall this famous topological characterization of the affine plane by C.P. Ramanujan. Accordingly, if we had all these properties were given by an affine surface, then that surface must be C2. So that every normal affine surface homomorphic to C2 must be C2. Whereas all these characterizations, these conditions, characteristics of the ring A, means A was satisfying all these characteristics, but it was not clear whether A is itself a polynomial ring. And because it was realized that it is very important to know whether this ring is a polynomial ring, because if you prove that this ring A is not a polynomial ring, it would be a step towards proving the linearization conjecture for the affine 3 space. So as I said before, this linearization conjecture was an open problem. It was posed by Kambayashi in 1970s, and it would have also, and if you prove that A is a polynomial ring in 3 variable, it would lead to the counterexample to the solution of the linearization conjecture for the C3, and as well as the Abhyankar-Sathes conjecture. So Abhyankar-Sathes conjecture was that if f is a polynomial in cxyz a polynomial ring in 3 variable, such that the hypersurf plane defined by f is actually an affine plane, then f must be a coordinate line. That is, f is a variable in xyz. So note that in this ring, if if this ring is a polynomial ring in 3 variables, then the fibers, if I put x is equal to a non-zero constant, then this y is can be expressed in terms of y, z and t, and this becomes a polynomial ring in 2 variables. And when x is a non-zero, x is equal to 0, then this is z square plus t cube, which is not a smooth, it's a cusp, so it's not C2. It cannot be a polynomial ring in 2 variables. Therefore, it is x can never be a coordinate, because all its fibers are not C2. And hence, if A is CXY, if A is a polynomial ring in 3 variables, then A is, will give, this would give a counterexample to the Abhyankar-Sathes epimorphism conjecture. However, it was proved by Makalimanov in a very important paper in 1996. He proved that this ring A is not a polynomial ring in 3 variables, and the major tool which he used was locomotion derivations and GA actions. So this eventually, so this Makalimanov proof was the idea was quite simple, that what he proved is that if small x denotes the image of capital X in A, then it's easy to see that small x is not a unit in A. Therefore, x is not a constant. And he showed that if d is any locomotion derivation on the ring A, then d of x is 0. Therefore, the Makaliman invariant of the ring A is not C, which must be the case had A be C3. Therefore, A is not C3. So this is a very simple idea. However, this proof was not so simple. Proving this statement that whenever D is a locomotion derivation, then dx is equal to 0. So this was quite involved. So Makalimanov gave this proof, and which eventually led to this solution of this linearization conjecture by Koras and Russell in 1996-97. They proved that any C star action on C3 is linearizable, and but of course the Abhyankar-Sathes conjecture is still an open problem. I now come to this asynchronous threefold. So let K be a field of positive characteristic and A be this ring. So where M is an integer, P is that characteristic of the field, and S is another integer where P does not divide S. And let R be the subring of A generated by X, where small x is the image of capital X in A. Then Asanuma had proved that this ring A is a stably polynomial ring over R. That is, if you adjoin one more variable to A, then this becomes a polynomial ring over its subring R. That is, A is a polynomial ring in 4 variables over the field K. Further, A is not a polynomial ring over R. He proved, Asanuma proved in 1987. And all the fiber rings of A. So even if it is not a polynomial ring over the ring R, all the fiber rings. So if you look at any prime ideal P of R, so all the fibers of A over a point P, they are all polynomial ring in 2 variables. So this example was constructed by Asanuma to give a counterexample to the A2 fibration problem over a PID. So this R is a PID here over a field of positive characteristic. And Asanuma constructed this example to show that A is not a polynomial ring over R, although all its fiber rings are polynomial ring. Just recall there's a theorem by Sathe, which is one of the major results and highly non-trivial result, which proves that if B is a principal ideal domain containing the field of rational numbers, then any A2 fibration over B must be a polynomial ring. So this was an example given by Asanuma to show that this condition B containing Q is very necessary. So this Asanuma again used this example to give a counterexample to the linearization problem in positive characteristic for n greater than equal to 4. So if and in 1994, this Asanuma proved that asked this question whether A is a polynomial ring in 3 variables over the field K, and because if you could show that this ring A is not a polynomial ring in 3 variables over K, then this would be a counterexample to the cancellation problem in positive characteristic for the affine 3 space. On the other hand, if you show that A is actually a polynomial ring in 3 variables, then it is a counterexample to the linearization problem for the affine 3 space in positive characteristic. And I showed that A is not a polynomial ring in 3 variables whenever this integer m is greater than 1. And hence, as a consequence, we showed this cancellation, Zariski's cancellation problem does not hold for the affine 3 space in positive characteristic. To give a solution to this problem, I made use of another invariant which is associated to the locomotion derivative, associated to a GA action, namely the Dukson invariant. And for me, the major tool of working was exponential maps, because I was working over a field of positive characteristic where locomotion derivation does not make much sense. So we studied exponential maps on the ring B. So this invariant was defined by Dukson, and it's a subring of B generated by all the elements which are in the ring of invariant of some exponential map. So if phi varies over all exponential maps on the ring B, then, and if F is a ring of in B phi, then the subring generated by that is called the Dukson invariant of B. And it's easy to see that the Dukson invariant of the polynomial ring Kn is Kn whenever this n is greater than 1. For if I set B is this polynomial ring Kxn up to Xn, and I define these exponential maps phi I of Xj, where Xj's where phi I sends Xj's to Xj plus delta Ij of U, that means it fixes all Xi's for I not equal, means it fixes all Xj where I takes Xi to Xi. The ring of invariant for B phi I is all those X1, Xn except Xi, and the Dukson invariant is B. Then using this, what I proved that the Dukson invariant of this ring B, this ring A, is a proper subring of A. However, if A were a polynomial ring, then the Dachshund invariant must be the whole ring. So hence, A cannot be a polynomial ring in 3 variables. So the major tool was exponential maps and Dachshund invariant, which led to the major breakthrough. Another important result in the area of affine algebraic geometry, which I proved using exponential maps and Dachshund invariant, is this theorem. So this is any arbitrary polynomial fxzt, and if I call g to be this polynomial and small f to the projection on the plane x equal to 0, then we proved that equivalence of this following 5 statements, that this ring is a polynomial ring in 3 variables if and only if it's a polynomial ring over the subring kx, or if f is a coordinate in kzt, or g is a coordinate in xyzt, or if x and g forms a coordinate pair in x, y, and z and t. So this study of this polynomial in 4 variables eventually reduces to the study of the polynomial small f, which is a polynomial in just 2 variables. And knowing whether A is a polynomial ring is same as knowing whether f is a coordinate in kzt, which is a much easier problem than this one. And hence, we have a solution to many important results, like it gives a partial solution to the Abhyankar-Sathe's conjecture, and it also proves in a very easily why this Russell-Koras threefold or this asynchronous threefold are not polynomial ring because of this characterization. These 5 statements are actually an outcome of 10 statements. The remaining 5 statements involves the Dachshund invariant of the ring A. So we proved that if the Dachshund invariant is the whole ring A, then all these statements are equivalent. So this is how I can say the utility of studying locomotion derivations and exponential maps. So I gave some application of G actions to the problems in affine algebraic geometry. G actions on its own has other important problems, like the study of Hilbert's 14th problem, or if you study the ring of invariant of a G actions, which was the original problem. So those are again very well studied problems. And unfortunately, I have not taken it up. Maybe I can talk more about it in the elaborated discussions. Thank you.